All right, welcome back for part two of the solving rational equations. We're into the lesson here, but actually we're further than that a little bit because we were reminded of some techniques in the 3-minute review. So, for instance, we're asked to use various strategies to solve rational equations, and we have, some rational expression equal to 2. This is f at x from the 3-minute review. It's this equation. So what we're interested in is finding where is f at x from the 3-minute review equal to 2. Well, one technique, and this isn't very accurate, but one technique I could use is to use a graph, right? If I wanted to, just where's y equal to 2? Right here. Right? There's y equals 2 around, and I know this is an estimate, but I can see there's a solution, there's a solution, there's a solution. Right? And I could estimate. In fact, if I did a better job of my sketch, I could use this as my whole equation solving technique is using a graph. When is this thing equal to 2? Here, here, and here. Those x values. Not very accurate, though. This is not very, I didn't do a good job with scale here, so I can't really use this. But it reminds me of a technique that we used when we did polynomial equations, is using the graphing calculator, right? I could graph y1 equals this and y2 equals 2, and then use the remember I could use the calc intersect to find out where those two values were equal to, right? Where that and that were equal to the f at x and y equals 2, left side and right side. So that's one technique. Now, of course, we're not going to focus on those. We're going to focus on the algebraic technique. And so what's the algebraic technique? Well, I want to solve this algebraically. How do I do that? Well, as long as the bottom's not equal to 0, as long as this is true, I can cross multiply, right? And that's what I'm going to do. What's kind of nasty about this, though, is after I cross multiply, beforehand, when this was finding x-intercepts, when y is 0, this got wiped out, and it doesn't. So it is a little bit nasty. This is now changed from a rational equation into a polynomial equation. So we have to remember all of our polynomial equation solving skills. And how we did this, expand, then move everything to the one side, and then I end up with a cubic function. Subtract 2x, subtract 4x, add 6, and I get that expression. Notice I can actually make this a little bit easier by dividing by 2. Oh no, I've forgotten how to do this. No, you haven't forgotten how to do that. Remember, this is a cubic. I can't factor it by grouping. So what I do is I call that f at x, and I use the factor theorem. And I try and find out when this thing is equal to 0. Factor theorem, for what values does that equal to 0? So if I remember, I always try factors of the last thing. So I try f at 1 or f at minus 1 or f at 3. And what do I get here? I get this is 1 minus, no, that's not equal to 0. Not equal to 0, so x minus 1, not a factor. And I keep going, right? I keep trying, and eventually I'll stumble upon f at 3, and that's 0. You can check it out. Bash that into a calculator. And then I get x minus 3 as a factor. So what do I do now? Long division. Long division. X cubed minus 3x squared, subtract, and I get x squared, bring down the 4x, plus x is is x squared minus 3x, subtract again, and I get negative x plus 3. This has got to be able to go and evenly, and it does. And so then, therefore, and I'm going to go back to this equation, star becomes, this is feeling a lot like a polynomial equation, but remember what I'm doing is I'm solving an equivalent polynomial equation to my rational equation. As long as the bottom's not 0, that equation and the equation that I'm solving using my Unit 1 techniques are the same. All right, well, where do we get? So that becomes x minus 3, x squared plus x minus 1 equals 0. And remember, I had to have the one side equal to 0 so I could use the factor theorem. This doesn't factor. I see one of my solutions is x equals 3. This doesn't factor, but it doesn't mean that it doesn't have any solutions. I'm going to use the formula. Use the formula with a is 1, b is 1, c is minus 1, and I get negative 1 plus or minus the square root of 1 squared minus 4 times 1 times minus 1 over 2 times 1 is negative 1 plus or minus square root of 5 over 2, which is about, if you bash that into a calculator, remember you got brackets there, two solutions, 0.62, and x is about negative 1.62. So that means my original equation has 3 solutions. My solution set was 3, 0.62, and negative 1.62. And let's just go back and check our sketch and see if those are believable solutions. 3, in fact, there was a 3, and we've got what was it, 0.62 and negative 1 point something. What was it? Negative 1 point, oops, 1.62. Yeah, that's believable. Dandy. So that actually matches our sketch. Let's keep going. For this one, example B, it's just like this example in the textbook, so I'm going to skip that one. Essentially, the idea is to still cross-multiply, multiply by the expression that will cancel all the fractions at once. And again, if you remind me, if you'd like to see my solution to example 1B, bug me in class, and I'll post that on the Facebook group. For part C here, again, the idea is we want to multiply by something that'll cancel all the fractions at once. This middle term, the bottom, is 1. So what expression do I need to multiply by to kill all the fractions at once? Well, I need to multiply by an x minus 1 factor. This one just has a 1, and I have to multiply by an x factor. So essentially, instead of 12, like we did in the 3-minute review, I'm going to multiply by this expression, x times x minus 1, in each case. And this step, by the way, you wouldn't actually write in. I'll show you what I'm expecting to see. So I multiply this thing by the common denominator, and then I multiply each thing by the common denominator. That will kill all the fractions. And then I simplify. And really, I wouldn't write this step in. What am I actually multiplying this one by? I'm multiplying it by the missing factor, x. And so here, x times 1 is just x. Here, in this one, well, I've got 2 times, nothing to cancel. On the bottom, I just have 1. So I've got 2 times x minus 1. And on this factor, well, that one cancels. It divides out, just like we divided into the 12 in the 3-minute review. And then I get the expression x minus 1 times 2x minus 1. And now I've got change my rational equation into a polynomial equation, and I can expand and solve. Now this is like a grade 10 question. It's quadratic. 2x minus 2 and minus 1 is minus 3x plus 1. And actually what happens here, look, when I put everything on one side, I get the 2x squareds canceling out. See that? Collect like terms. That's negative x. Add 3x to both sides is 2x equals 1. And I finally get the solution x equals a half. Dandy. Notice that if I wanted to, I could substitute in x equals a half and see the left side is equal to the right side. Another way I could do that, remember, if I wanted to check this graphically, I could put y equals this big expression into a graphing calculator and y equals this big expression in a graphing calculator, and they should cross at that one spot, x equals a half. All right, remember to read this example from the textbook, and you can do your own solution for that one and bug me for my solution if you'd like. There are a few from the textbook to try, and of course an FAQ.